Hello, welcome to a new virtual tour of the European Southern Observatory, or simply ESO, its acronym. My name is Farid Char, and with the producer Hector Salas, we are going to be your guides during this trip to the ESO Paranal Observatory. Um, so just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the I am one of the guides of the Paranal Observatory since 2010, and I am also part of the staff of an astronomy center in the University of Antofagasta. And one of my main hobbies is astrophotography. So, as I told you already, I am not alone. I am with the producer, Hector Salas. So, how are you, Hector?
Hi Farid, I'm happy to be here once again. So I'll introduce myself to our audience. I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam, Germany. I work mostly with topics related to the circumgalactic medium, that is the environment that surrounds the galaxy. And I joined the team of guides for Paranal Observatory in 2019 while I was doing my master's in Antofagasta. And today I'm going to be the producer, and that means that I'm going to play the videos, change the pictures, but also be gonna be reading all your comments and all your questions. And during the tour, Farid will have some interest to answer them all. And please send any questions you have, any comments.
Okay, thank you, Hector. It's a while to be with you during these virtual visits and bring astronomy directly to your home or wherever you are. So please remember you can send your questions or comments during this streaming. So you can use the comment section in Facebook or YouTube. I imagine you already have several questions, so you can send your questions, and during some parts of this virtual experience, we are going to answer them. Okay. Now we are going to start with this tour, and the first thing I am going to do is to help you to understand the place of our visit. So we will begin with some information about the European Southern Observatory, or ESO. So now you will see a picture in your screen regarding the member states. So ESO is composed of 16 member states. The headquarters of ESO are located in Germany, and also Australia has also joined ESO as a strategic partner. In this case, Chile is the host state and is the home of all ESO observatories. So from the 1960s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories, such as ESO, to our country. As a result, Chile offered its territory, and ESO did choose the more suitable areas. Okay? So in this case, the mission of ESO is to design, to build, and operate astronomical observatories. And why? Well, to enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. So right now you will see a picture with the three observation sites of ESO in Chile. So first we have the Chajnantor Plateau. This is the site of the ALMA and APEX radio telescopes. ESO is part of those places for radio astronomy alongside other international partners. Additionally, south of the Atacama Desert, at 2,400 meters above sea level, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes, such as the NTT or the 3.6 meter ESO telescope. And this one is using the HARPS instrument. And this is an exoplanet hunter. So finally, we have the place of our visit today, the Paranal Observatory. This ESO observatory is the home of the Very Large Telescope, or VLT. This is the most advanced visible light telescope on the planet. In the next few years, we will also have the Extremely Large Telescope, or ELT. This is the biggest visible light telescope on Earth. And also near there, the CTA will be an array of telescopes focused on capturing gamma rays. Okay, now we have a better picture. So right now we are going to travel to the Paranal Observatory. So we will have an animation. Okay, this one. So now virtually, you are flying over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital Santiago. Specifically, about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Taltal, the closest city. So now we are going toward the mountaintop of Cerro Paranal, located at 2,600 meters above sea level. This mountain belongs to the coastal range, and despite its altitude, it is located at just 12 kilometers from the coast. But where is the ocean? Well, the Pacific Ocean is located below of the cloud cover over there. But why those clouds, if right here the sky is so clear, dry, and lonely? Well, this is because of the influence of the Humboldt current. This is a cold current near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level, keeping below the cold, humid, and basically bad air for astronomy. About the layer, instead, we have the hot, dry, and less dense air. So this is something like the good air for astronomy. The clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. Okay, but what about other natural barriers around this area? Well, about 200 kilometers to the east, we have the Andes Mountains, with very high mountains, with more than 6,000 meters above sea level. So this is another natural barrier blocking the clouds from Argentina and Bolivia. So the main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. Also, here we are far away from artificial light sources because of human activity. I mean, light pollution. So, this is one of the best places on Earth for astronomical observations. Okay, so right now we will change the view to have an even closer look to Paranal. Okay, so as you can see here, this is not an ordinary mountain. And now we can see the different telescopes and structures in the mountain. We are at the summit of Cerro Paranal. Do you know what Paranal means? Well, in the Quechua language, Paranal means whirlwind, possibly because of some whirlwinds forming in the desert. However, as I told you already, the atmosphere here is extremely quiet. This observatory is a true oasis. As you will see how in one of the driest deserts, we have a lot of life and a lot of science. Okay, so right now we will visit the summit of Paranal. Okay, so here we are, and right now in front of us we have the Very Large Telescope, or VLT. It's acronym. So if you see the amount of buildings here, four giant domes and other four small and rounded ones, it is clear that the Very Large Telescope It's not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. So let's take a closer look. Here you can find the four unit telescopes or UTs, each one with a primary mirror of 8.2 meters of diameter. So basically the giant ones in your screens. And the other small ones, I mean this one, okay, and this one, and those ones, are the auxiliary telescopes, or ATs, each one with a primary mirror of 1.8 meters of diameter. So each UT has a name in Mapudungun language. This is the language of the Mapuche culture, natives from central or south of Chile. So here we have Antu, which means sun. Here we have Cuyen, which means moon. Here we have Melipal, which means four stars, but this is related to the Southern Cross constellation. And here we have Jepun, which is associated with Venus as a concept related to the evening star. And the closer ones, as I told you already, are the auxiliary telescopes. They are mobile and they can be moved using a rail system. This one. We can move them up to 30 different positions. They were specifically designed to work all together as a single big telescope with a variable diameter, able to reach up to 200 meters, as you will see in a few moments in a short video. Okay, so this is the video. So basically, this technique to combine light from several telescopes is called interferometry. So we are able to observe much more specific details if you compare this with the individual telescopes. Now, thanks to interferometry, we can simulate a giant mirror to distinguish details um, up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. Okay, so right now we will come back to the tour screen. Okay, so now you will have the opportunity to visit a telescope. In this case, we are going to visit this one. We are going to visit UT3 or Melipal. We can't enter all the telescopes, but don't worry about that because the four ones are identical in size and shape. So the only difference are the instruments inside. Now, you can know more about the instruments on the ESO website if you want to know more information. Okay, so now we are going to enter UT3 Melipal. And here we are. So now we are on the UT3 telescope. So what can you see? Well, this is a giant telescope. Okay, so we are on the last floor of the telescope at the same height of the main mirror in front of us. This mirror has 22 tons with 8.2 meters of diameter and only 17 centimeters thick, created from a ceramic and flexible material called cerutur. And in addition to that, I am doing a close-up. The reflective surface of this mirror is a very thin layer of aluminium. So this reflective surface here is a very thin layer of aluminium, only 80 nanometers. So it's very, very thin. Okay, so this is the situation with the mirror right here. This is the primary mirror. But now, how can we point this telescope to the sky without breaking it? Because as you can see, it's a very big telescope. Okay, so we are going to check the mirror and the telescope from another angle in order to explain that. So I am going to change the view and I am going down to this level to explain this. So I am going to show you the telescope from this position. Okay, so look at the telescope from this position now. So from this position, you can see that the mirror is mounted over this white structure. Can you see it? So this is a cell supporting all systems assisting the mirror, including something called active optics. And here you can see some little gray boxes, these ones. Okay, so I am going to do another close-up. So you can see those boxes. So the boxes are called actuators. They are a kind of piston, and we have 150 in total. All of them are controlled by a computer. So they are acting on the mirror during the observations in order to keep the optimal shape of this concave mirror. Otherwise, it could suffer deformations just because of gravity. Those deformations, imperceptible in a first view, could be critical in the result of the observations. Now, how is this working together? We are going to return to the previous screen to explain that. So we are going to change the view again to show you the telescope from this position. And from this position, we are going to explain very shortly how this telescope and the mirrors are receiving light. So we are going to show you a short animation to explain that. Okay, here we are. So basically, the first step is to open the dome. Okay, of course, this is exaggerated here. So after that, the primary mirror will receive the light, the 8.2 meter mirror. The light will be concentrated and reflected to the secondary mirror in the top, and then reflected again to a tertiary mirror in the middle, and the light will be finally reflected to reach one of the instruments. And here you can see the instruments represented at those boxes, like the red, the blue, and the green squares. So we have three different instruments, okay? And we can use one instrument per time, per observation. And the instruments will be in charge of converting the light, the physical light, into a digital picture. And the digital picture or the digital signal will be transferred by fiber optics to the control room. So basically, the astronomers and all the scientists are working from another location. They are not physically inside of this telescope. So this is what happens in real life in an observatory like this one. Now, what happens in this telescope the rest of the time? So during the day, we have some engineers. For example, in this picture, you can see some people, some engineers working because they are basically preparing the telescope, fixing problems, doing maintenance in order to prepare the telescope for the next observation night. So that's why we have engineers here during the day. But during the night, this place is completely empty. It's in darkness because we need to do a remote control of the telescope from the other location. This location is called the control room. And here you can see one of the instruments. So as you can see, it's a very big machine. Um, um, and as I told you already, we have one here. Another one is located on the other side. And one last instrument could be placed here in the base. Okay. Okay, so this is basically what happens here. This is the regular explanation about the telescope and the instruments. So now we are going to come back to the previous screen, I mean to the telescope platform, because we need to keep moving. And we are going to visit virtually the control room. So we are going to move to another location, and this location is basically here, this one. So the control room is located physically in the mountain top, but not in the same level of the telescopes. So it's basically like this in a different level. So the control, this is the control building. It's a big building. Here is another angle to show you from the opposite side. This is the control building, and the last floor here, you have the control room to do the remote control of the telescopes. So this is the next step, the next, the next stop of this virtual visit. But before going there, I think Hector, we have some time in case we have some questions. So Hector.
Yeah, we have several greetings. Have here Spoon saying hi, Roman saying hi to all friends, Buen dia from Nicolas, Swig Raven sending us love from Amsterdam. We also have someone from Finland, from Italy, the province of Modena, and we have Jose Urquendo from Florida, who asked us about how high is La Silla telescope at sea level, and if we have some videos, some photos that we can watch for that.
Well, La Silla is another observatory. Is located uh, more or less near La Serena city, and La Silla is located at 2,400 meters above sea level. But in the case of Paranal specifically for this tour, the mountain top of Paranal is at 2,635 meters above sea level. And regarding the videos and pictures, well, basically you can find a lot of videos and pictures from in the ESO website. So you can visit basically um, ESO.org, and you can find a lot of media.
Yeah, you can have hundreds of photos, videos, and also this 360 tour that we are working here for La Silla. And also, since you asked about La Silla, we also make virtual tours for La Silla Observatory, not just Paranal.
Sorry, say again.
That I just want to tell our audience that we also do these virtual tours for La Silla Observatory.
Oh, yeah, sure. So
Yeah, so
basically we are alternating. Yeah.
yeah. Yeah. Last week was La Silla. This week is Paranal's turn. Okay, we don't have any more questions so far, so let me ask you one of the usual questions that people ask in the in-person tour. What kind of maintenance do you need to do on the mirrors?
Yeah, we have to do some important maintenance on the mirrors in order to keep the mirrors clean. So in order to explain that, I'm going to revisit the telescope here. So basically, we have to do well. We have two types of um, cleaning systems. One of them is like the easy way or the easy cleaning, and this involves to rotate a little bit this telescope, and a couple of engineers will work to spread a carbon dioxide snow on the mirror. So this is something like a foam, and this carbon dioxide will remove dust. Okay, so because well we are in the desert and we have dust in the environment, so the carbon dioxide will remove dust, and we can keep the mirror, let's say, clean. And we need to do that about once a month. Okay, but as I told you already, it's like an easy process. You don't need a lot of resources. You don't need a lot of people doing that. But this is something like an easy cleaning for every day. Now we have a more complex way to clean the mirrors, and this involves to remove all the mirror from this building. You need to extract the mirror, this mirror, and the white cell. You need to remove all of this. And in order to remove all of this, you need to use a special crane. So basically, you need to extract the mirror to the outside through a special door. And in the outside, I will show you from this perspective. In the outside, you have something. You have well, maybe you can see this yellow thing here. This yellow thing is something like a platform to receive the mirror when the mirror is in the outside, and at the ground level we have a special vehicle. It's like a big truck. So basically this vehicle will receive the mirror because this platform will basically drop the mirror very slow, very slow, very slow. So the vehicle will receive the mirror, and this vehicle has to go down with the mirror, of course driving at a very slow speed. And we have to transport the mirror to another facility in the base camp. So in the base camp, we have to well, transfer the mirror to this mirror maintenance building. And in the mirror maintenance building, the mirror um, will go for a recoating. So what's the recoating? Is basically uh, a process when you need to remove the aluminum layer, um, and we need to put a new one, a new aluminum layer. So basically, after this process that takes about 3 or 4 days, the mirror looks like new because, well, basically you are changing the reflective surface. So the mirror looks like new. And after that, we need to place the mirror again in the vehicle. The vehicle is coming again to the platform. We have to put the mirror again in the telescope. So we have to lift the mirror and we have to place the mirror in the telescope, and the mirror is basically ready again for observations. So this is what happens with the mirror, and all this more complex maintenance is something like every 2 years, something like that. But this is our way to keep the mirrors clean.
Okay, thank you for it. And we have one last question here. User 123 is interested in gamma rays. Uh, can you tell us something about gamma rays observation?
Well, I can give a very, say, quick overview. Is gamma rays are basically one kind of energy uh, in the universe, and basically in astronomy you have some kinds of special events. Sometimes gamma ray bursts, and like a very energetic events in the universe, and some uh, telescopes facilities on Earth are trying to well, observe that. But of course, as I told you, gamma rays are a kind of energy in the universe, uh, but you cannot see the gamma rays with your eyes, so you need some special kinds of instruments to observe that. You cannot do that with Paranal, so you need a special kinds of instruments that are specifically designed for gamma rays. So maybe you can maybe give complementary a little bit more with this.
Uh, well, maybe just to mention that the CTA array is going to be observing gamma rays, right? And that's going to be
Yes,
very close to Paranal, like between Paranal and the ELT.
correct. So
Yeah.
so so basically, the CTA is a collection of telescopes that will detect the gamma rays from space. But in this case, is something uh, not associated completely. It's not associated with ESO. It's another organization. By the way, the CTA is an acronym of the Cherenkov Telescope Array. So yeah, that's the approach of
Mhm.
this new project.
All right. I think we can continue and we will have a second opportunity to answer more questions. So if you have any more comments or questions, please keep sending them. and we'll try to answer them.
Yeah, sure, sure. Okay, so we are going to continue with the tour, and we are going to move to the control building. So we have the control building here, and we are going to basically visit the this the workplace for astronomers, because this place, as you can see, is, well, it's a very normal place. It's like a big office, and from this place you have the scientists, you have the telescope operators, you have the astronomers. So basically, the control room is a place to work during the night. Okay, and you can see that this place has different workstations, and each workstation is dedicated to one single telescope. So, for example, this workstation is specifically designed to work with Melipal UT3. So all operations with Melipal are from here. So you can see a lot of computers and people here, but they are specifically working for this telescope. In the opposite side, we have another workstation, and this workstation is for UT4 Jepun. So all operations with Jepun are from here. So the same, you have a lot of different computers, and you have some people working, and they are working specifically on the UT4. Now, if we continue through this virtual corridor, we can take a look at the other workstations, and you have this workstation here. This one, this one belongs to M2 UT1, and so only operations with M2 are from here. And in this other station, this one, you have all operations with QGen, with UT2. So basically, this is what happens here. All the telescopes, instruments, and systems explained before are controlled from here. So during the day, engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. So each night, we have a telescope operator and an astronomer per telescope. So, for example, if we go closer, if we take a closer look at this workstation, we can see, well, the same, many computers here. This person is a telescope operator, okay? And let's say that maybe this person is astronomer. So the telescope operator is the person in charge of the technical details and the movement of the telescope. So it's something like the pilot of the machine. The ESO astronomer is, in this case, in charge of directing the scientific observations, and this person will decide the next steps. So it's like the co-pilot. Now, the observations are performed by experts from ESO for scientists from all the planet. Okay, so this is basically what happens here. This place is, of course, is much more comfortable. Is warm. You have all the necessary things for working all night, but it's basically an office space. Okay, so now we are going to come back to the VLT platform again, because at this point you know much more information about the observatory and the people working here. But now I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean, from La Silla, Paranal, and Chacnantor. So, scientific staff from different countries are using the ESO telescopes to study objects near to our home, the solar system, but also others located in the more distant places in our universe. Okay, so now we are going to explore a list of the top 10 discoveries from ESO sites so far.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Well, this was the top 10. Of course, it was very impressive. But we have just one more thing. We have like a bonus track. So let's take a look at this now. It's another short video. Okay, here we are. So a team of astronomers, in this case, was able to capture the first image of a black hole. This was a very important discovery a few years ago. The Event Horizon Telescope, or EHT for its acronym, it's an array of 8 ground-based telescopes distributed on the planet, working as an international collaboration, and they were able to achieve the first direct evidence of a supermassive black hole. So the picture you will see at the end of this video reveals the black hole in the center of Messier 87, a massive galaxy in the close galaxy cluster in the Virgo constellation. This object is located 55 million of light years from Earth, and its mass is about 6,500 million times the mass of our Sun. Okay, so we hope you liked the top 10. This was only a fraction of the discoveries thanks to the ESO telescopes and the scientific stuff behind them. So now we can continue, and from this platform again, we are going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. So as you can see here, the sky is almost completely dark with the last traces of light from the twilight. The moon is below the horizon and the sky is full of stars. So here we can see a very popular constellation just above the AN2 telescope. So we are going to do a close-up here. And here we have this constellation. It's a very popular constellation. This is Orion. In the mythology, Orion represents a hunter. Now you can recognize this constellation because of those 3 stars somewhat aligned, representing Orion's belt. And inside of Orion, we can see another interesting object. This is the Great Orion's Nebula. Okay, so these are of course very popular objects of the night sky. But now we are going to change the position and move to the brightest star of the night sky. This star is called Sirius. So this star belongs to the Canis Major constellation, and this one represents Orion's hunting dog. So basically the constellation of the Sirius, okay, is in the mythology connected to Orion, okay, this one. Okay, so now if we come back down, a little bit down, and next to the AN2 telescope, we can see another important object. So basically here we have the Pleiades. Pleiades is an open star cluster, and this cluster is located in the Taurus constellation. Now, the majority of those objects are visually close to a specific area. An area with a lot of stars is much more populated with stars, this one, because, well, of course, here you have much more stars if you compare with this area of the sky or this area of the sky. So this area is one of the Milky Way arms, our galaxy, and our sun is only one among hundreds of millions of stars. So during the winter in the southern hemisphere, we can see the center of the Milky Way. And this is another area full of stars between Scorpius and Sagittarius constellations. And you can see all this area from this hemisphere, from the southern hemisphere. Okay, so now we are going to change our view and we need to move to another sector in the sky. So we are going to find two spots in the sky. We are going to change the view now, and here we are. Those spots there are the Magellanic Clouds. So up there we have the large Magellanic Cloud, and down there is the small Magellanic Cloud. Okay, so they are not actually clouds, of course. They are galaxies with an irregular shape. Both of them are visible to the naked eye in a clear night like this one. Um, and those galaxies are orbiting our Milky Way. So they are basically satellite galaxies of the Milky Way. Okay, so this name, the Magellanic Clouds, refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, the people were absolutely unaware about what a galaxy is. Okay, so another area right here next to the Magellanic Clouds is the smallest constellation in the sky. This one. This is the Southern Cross. So we are going to do a close-up, and this is the Southern Cross. It's tilted here. This constellation is visible all from the southern hemisphere. It's very easy to recognize this one. And this one is an important constellation to find the South Celestial Pole. The South Celestial Pole is basically a projection of the Earth's south pole. So during the night, the stars appear to revolve around this point. So to find this point, the South Celestial point, the South Celestial Pole, we have to extend in our imagination the longer stick of the Southern Cross, this one. And we have to extend this longer stick about 4.5 times. So we are going to do that. We have to extend this something like 1, 2, 3, 4.5, and more or less like here, you have the South Celestial Pole. So this sun, if you look at the horizon from this point, I mean like here, basically you are looking at the south cardinal point. Okay, so this is a very interesting way to find your south cardinal point. Okay, so with this information, we are concluding our visit to Cerro Paranal, I mean to the mountaintop. So now we are coming back to the platform in the daytime. And the last part, the last stop of this virtual visit is a more relaxing place. Okay, basically we have to come back and to go down because we have to go to the base camp located at 2,400 meters above sea level in order to visit a very special oasis. So we are going to go there, and this is the base camp. It's basically a place for all the people working here, something like 130 people. And we have a lot of important facilities, such as rooms for contractors, the meter maintenance building, some offices for the informatics, for logistics, a warehouse, mechanical workshops, etc. But the place I want to show you is located here, and this is the residence of Paranal. So this is the place where the ESO staff can stay and rest. So we are going to move there. So this is the entrance. The residence is the home of the ESO staff when they are walking in the desert. And in order to access, you need to use this ramp. This thing like a dome, is like the roof of the residence, and it looks like an underground facility, but but it's not like that. This is actually taking advantage of the shape of the land. So you have the entrance here using this ramp, but in the other side is like a normal building. Okay. Okay, so we are going to enter, and here we are. So basically, here in the residence, the workers can enjoy a more humid air. They have a swimming pool, they have green areas, and also very nice environment compared to the desert and the intense sunlight from the outside. So from here you can see, um, for example, you have the restaurant over there. All the workers can go there for eating. Here we have the lobby, and here we have the reception. So this is very similar to a hotel, but this is only for the staff. And through this corridor, you can access the rooms. We have 108 rooms in this residence. Okay, so during this time at the residence, and because this is the last stop of this visit, we have some time to answer the last questions. So, Hector?
Okay, so we have some extra greetings. We have GT Telera saying hello from Hungary. We have Pavel Lech from Poland. He's asking us how year was built the VLT? In which year?
Well, the VLT construction began in 1991 and was finished in 1998. At this time was the formal inauguration, so it was 7 years of, of construction, and the first light one in 2000. So it was a lot of time.
Okay, we have a question from Pablo Stefani. How many people work there? Well, you already mentioned that about 130.
Yes, correct.
Yeah, and most of them are not astronomers. They are engineers or people working in logistics and things like that.
Exactly. So only about 10% of all people in Paranal are actually astronomers, but the others are, yeah, as you say, the engineers and other people.
Okay, I have another question from GT Talera. What kind of techno signatures can ESO detect? Okay, that's an interesting question. Okay, so techno signatures, these are signals of technology somewhere from a different civilization that could be out there. So, not easy to answer. I mean, people have done the experiment of simulating what would happen if we observed the Earth with our current telescopes, either ground-based or space-based, and see if we could detect life or not. And it's not easy, particularly because in the past, we sent a lot more electromagnetic radiation into radio waves and TV waves, but now a lot of those things are cable-based and not just floating outside. And we could try to observe something like a Dyson sphere in the infrared or something like that. But at the end of the day, it's going to depend on the wavelength that we have access in each observatory and whether we can observe some signature in that particular wavelength. But this kind of thing is mostly the kind of observation that SETI does more than the work that is usually done with ESO observatories. I hope that answered a bit the question. We also have some greetings from Jose Maria. And when Paulo Stefani is asking about these live streams, well, we're live right now, and we are doing this live stream every Saturday. We are alternating between Spanish and English, and also between La Silla Observatory and Paranal Observatory. And to know exactly which next virtual tour is going to be, you need to keep an eye on our social networks. And we have lastly a question from David Orlando. how long was the supermassive black hole observed? So I was trying to look the answer for this, and I found that there were two different campaigns of observations in 2017 and 2019. These were about 5 nights each, and they tried to observe for approximately 8 hours each night. So 8 times 5, about, that's 40 hours observation, times 2 because of the 2 years, so about 80 hours. So a lot of observation time. And okay, we also should mention that this observation time is not necessarily only the black hole itself, maybe some also calibration images as well. So I hope that answers the question. And I think that's all the questions that we haven't answered so far.
Okay.
Good. Okay, so I would like to remember everybody that we have the spiritual tours every week, but we also have the tours in person. If you have the opportunity to travel to Chile, you can go to Paranal Observatory or to the Observatory. These tours are completely free, but you need to sign up in a website first, and you need to get to the observatory by yourself. Maybe you can tell us a bit more about this, Farid?
Uh, no, well, just to say that it's completely free, and but you have to book in advance because we have a lot of people wanting to go there. So try to book in advance, maybe 2 weeks in advance at least, to get a spot. Okay. Well, so we are approaching the end of this visit. So we remind you that all this information, pictures are available on the ESO website. And so in this way, we start to say goodbye. So I hope you like this virtual experience. So please stay alert to the ESO social networks to know when we will have the next virtual tour. So on behalf of ESO, from my side, I want to say thank you very much for your presence. Thank you and goodbye.
Goodbye.